Today we'll discuss certain applications of Huygens Principle. In a previous lecture entitled 2a, we discussed Huygens Principle and Huygens Fresnel Principle. We'll study application of Huygens Principle in case of laws of reflection, laws of refraction. Also, we'll study application of Huygens Principle for light passing through an aperture as well as light passing through two apertures. It is customary to deal with laws of reflection first and then to take up laws of refraction. But I feel that if we first try to prove laws of refraction from Huygens Principle and then take up laws of reflection, it will be an easier task because the diagram involved in case of refraction is simpler and easier to follow. So let us try to prove the laws of refraction starting from Huygens Principle. This is an interface M1, M2 which separates two media. One is rarer, one is denser, and the rarer medium has refractive index N1 and that of the denser medium is N2. So obviously N1 is less than N2. Also, let us be reminded of the fact that velocity is lesser in denser medium and greater in rarer medium. And this is the incident ray which strikes the interface and goes into the target medium where the ray bends towards the normal. So this is the phenomena of refraction, and the two laws are incident ray, refracted ray, and the normal to the plane of incidence are coplanar, and the famous Snell's law which says that N1 sin I is equal to N2 sin R. Now consider a plane wave incident on an interface M1, M2. So this is the interface M1, M2 and a plane wave is incident on it. Now let us go over to the next diagram. So these are the rays. We have drawn 4 rays and wavefronts are normal to the rays. So this is the wavefront. The wavefront is advancing towards the target medium which is refractive, which has refractive index N2. The representative wavefront we have shown is A, J, K, P, and this is the position of the wavefront at time t equal to 0. Wave moves with speed v1 in this medium, and therefore in time delta t it will move a distance of v1 delta t. Now, according to Huygens principle, if we know the position of the wavefront at t equal to 0, we can construct the position at any future time by drawing spheres which represent secondary wavelets. So let us first try to understand the diagram. At t equal to 0, this is the position of the wavefront. After elapse of time delta t, the wave advanced by an amount v1 delta t, and therefore to get to the new position we have to draw spheres, secondary waves, and this is the sphere. With respect to k as center, we have drawn another sphere, with j another sphere, and then we have to draw a common tangent. So this is the position of the new wavefront in medium 1 where it has advanced by a distance v1 delta t. Now we see that at point A the wavefront has struck the interface. Now just as these points, A also will send waves, but it will send waves to the second medium, and therefore we have to draw, as in these cases, spheres of secondary waves. Here the radius of the sphere was v1 delta t because j, k, p are confined in the first medium, but A has finished its journey in the first medium and it is now embarking on a journey in the second medium, and therefore it will send waves in the second medium, and they are obtained by drawing spherical secondary waves of radius v2 delta t. In the same time in which P moves to Q, K moves to L, J moves to B, A will proceed or advance in the second medium, and this is the radius of the secondary wave which A emits but into the second medium. Let us consider a further elapse of time delta t, and therefore through the same procedure we can draw further secondary waves, spheres of radius v1 delta t with center at Q, with center at L, and join these points, that is the common tangent or envelope, and therefore this is the position of the new wave front after elapse of time delta t plus delta t twice delta t. Now B has now struck the interface and it will start sending waves in the second medium, and therefore we can draw secondary wave spheres of radius v2 delta t, because speed in this medium is v2. So in the same time delta t, this will send waves in the second medium, and the radius of the secondary waves will be v2 delta t. But what about A? A was already here. The waves that A sent in the previous delta t, it came up to here. Now in a further time delta t, it will be sending waves further into this medium. So now we can draw another sphere of bigger radius v2 into twice delta t to get this sphere, half sphere rather. Now after elapse of a further time of delta t, R will come to D again by the same procedure of drawing secondary waves, spheres of secondary waves. Now C has struck the interface, and therefore C will now be the center of secondary waves of radius v2 delta t, and B now will send waves, secondary waves, and the spheres are of radius now v2 twice delta t, and A will now send secondary waves having sphere radius v2 into thrice delta t, because here delta t plus delta t plus delta t is thrice delta t. So in a nutshell, what happened is at t equal to 0, A, J, K, P was the initial position of the wavefront. After elapse of time thrice delta t, this wavefront has completely entered into the target medium and it has taken the position EFGD. How did we get it? This is the common tangent to these secondary waves as per Huygens principle. So this is the refracted wavefront EFGD, and the incident wavefront was AJKP, and the radius here is v2 into thrice delta t. Now let us draw a simplified diagram, the same diagram, but we'll draw it in a simpler way. So this is the diagram. Here M1, M2 is the interface, and these are the rays IA and one parallel to it. So these are the rays. This is the incident wavefront AP. Here we had AJKP. We are not showing these 2 points. We are showing just A and P for simplicity. So this is AP, which is the incident wavefront. Now after elapse of time, say 3 delta t, we have taken here 3 small instants, and therefore we are using this 3 delta t. So after elapse of time 3 delta t, the wave from P has advanced and reached D. The wave from A, but in the first medium where it had velocity v1, but the wave from A has advanced by a distance v2 into 3 delta t in the same time, 3 delta t, and therefore we have drawn a secondary wave sphere with this radius, and the envelope, that is DE line, will represent the refracted wavefront. So the diagram is, I think, clear. We have defined all these things, and this is the ray DR1, is perpendicular to the refracted wavefront. So this is the ray of the refracted wavefront. The calculation is extremely easy, but understanding the diagram is very important. The explanation is written in this sheet. We will now derive the laws of refraction referring to this diagram. The incident wavefront is AP, the ray is IA, the refracted wavefront is ED, and the refracted ray is DR1. The normals drawn are AN1 and DN2 with respect to the interface M1, M2. Angle of incidence will be, if this is the normal and this is the ray, obviously this one is the angle of incidence. And if this is the interface and this one is the wavefront, this is the angle of incidence of the wavefront. Also, if we consider the angles shown here, this is 90 degrees and this one is 90 degrees, which means this angle and that angle are same. So this is I, this is I. So I is the angle of incidence. Now what about the angle of refraction? Here this is the refracted ray, this is the normal, so this is obviously the angle of refraction. This is the refracted wavefront and this is the interface, so obviously this is the angle of refraction. And further, if we look at the angles involved here, this is 90 degrees, this is 90 degrees, so it is clear that these two angles are same. Now let us focus attention to these two triangles. One is this right angle triangle and this is right angle triangle. Why is it 90 degree? Because it is a ray and it's a wavefront, so it is obviously 90. And why is it 90? Is the tangent, and tangent makes an angle with the radius of amount 90 degrees. So this is a right angle triangle, this one too is a right angle triangle. Now let us try to find the value of sine of I. Now sine is perpendicular by hypotenuse, sine of I is therefore PD by AD, and sine of R is perpendicular, that is AE divided by hypotenuse, that is AD. Now as mentioned earlier, these lengths PD is V1 3 delta t, V1 because it is in the first medium where velocity of the wave is V1, and this distance AE is V2 into 3 delta t, V2 because it lies in the second medium where wave has velocity V2, and AD is common, so we have written V1 3 delta t for PD and V2 3 delta t for A. Now it's very easy to find the ratio. So sin I by sin R is V1 by V2. Now from the definition of refractive index, we know that N1 is C by V1, C being the speed of light in free space, and similarly N2 is C by V2, and therefore if you take the ratio we get N2 by N1 as V1 by V2, and therefore sin I by sin R, it follows from this relation that sin I by sin R equal to N2 by N1, and therefore we get the Snell's law. So this is the Snell's law, which we have obtained extremely easily using Huygens principle. We note that the incident ray is perpendicular to the incident wavefront AP. The refracted ray DR1 is perpendicular to the refracted wavefront ED, and the normals AN1 and DN2 are perpendicular to the interface M1, M2. Since this set is perpendicular to all of these, so they are also coplanar. So this proves the first law of refraction. So it follows that we have been able to derive law of refraction starting from Huygens principle. We also note the following, that V1 by V2 in unit time can be taken to be the ratio of the distance in medium 1 to distance in medium 2. Now the thing that is moving is a wave characterized by a wavelength. So distances are proportional to the wavelengths. So v1, v2 can be taken to be equal to lambda 1 by lambda 2. Now if we put this ratio in the relation that we obtained, we get this very important formulae. Now v1 can be written as nu1 lambda 1, v2 can be written as nu2 lambda 2, where nus represent frequencies in medium 1 and medium 2. Then since lambda 1 by lambda 2 are on both sides, they cancel out and we are left with nu1 equal to nu2, which means frequency is fixed. Now this is a very important result, and we can say that when light moves through different media, its frequency remains fixed. What changes is, from this relation it is very clear, to keep nu fixed, things that will change are v and lambda. And if v and lambda both either decreases, which happens in a dense medium, or both increases, which happens in a rare medium, all these to keep the frequency fixed. Let us now apply Huygens principle to prove the laws of reflection. Reflection is a phenomena which occurs in the same medium. Incident ray gives rise to a reflected ray, and along with the normal, these rays are coplanar, and the angle of incidence and angle of reflection are same. Now let us consider a plane wave incident on a mirror, which is m1, m2. Let us first try to understand the diagram, which is exactly identical to the diagram we drew in case of refraction. The only difference being all the drawings are on the same side, but in case of refraction we had a part on the lower medium and therefore it looked simpler. But essentially, if the diagram for refraction is understood, this one will follow along the same lines. So this is the reflector m1, m2, and these are the rays. So IA is a ray, and the wavefronts are perpendicular to this ray, so we have these wavefronts. At t equal to 0, AP is the position of the wavefront. Now after elapse of time delta t, P comes to Q, K comes to L, and J comes to B. How do they come? According to Huygens principle, with center at P, we have to draw spherical wavelets, and then we have to draw a common tangent. So that gives rise to BLQ, which is the position of primary wavefront after elapse of time delta t. So the primary wavefront was at AP, and after time delta t, it has advanced to the position BLQ. Now when P comes to Q, K comes to L, J comes to B, and A will also try to advance to this position, but since it is blocked by this interface or mirror, it will not be able to send wave downward, and therefore it will get reflected and it will send waves in the same medium vertically upwards, and therefore we have to draw secondary wave sphere, and the radius of which will be equal to this amount. So V delta t is the distance that P has approached or advanced in time delta t, and since A and P are in the same medium, the wave from A will also advance by a similar amount. So we have drawn a secondary wave sphere of radius V delta t, and therefore this secondary wave has resulted. Now if after a further elapse of time delta t, Q sends secondary waves, and with center Q we have drawn these wavelets. Similarly, with respect to L also we can draw another wavelet, and then you have to draw a common tangent that gives us CR. But by the time when Q goes to R and L goes to C, B cannot go here, and therefore B will send waves in the same medium vertically up, and therefore we have to draw a secondary wave of radius V delta t by the same amount V delta t, and therefore we get this secondary wave sphere. And what about A? A earlier sent secondary wave of radius V delta t, but now to it we have to add further time delta t, and therefore it will emit or emanate secondary waves having a larger radius of amount V twice delta t. Now R goes to D after elapse of a further period of time, say delta t, this distance being V delta t. This is that wavelet sphere, and in this period of time C cannot go here, and therefore C will emit wave which lies on a sphere of radius V delta t, and B now will emit a spherical wave of radius V twice delta t, and A will emit a secondary wave sphere having a radius thrice delta t. Earlier we were here, so now it will be V thrice delta t. So to sum up, P goes to D and the distance is V into 3 delta t, and in the same period of time the wave from A will go to this sphere having radius V 3 delta t, the same distance. Now by Huygens principle of construction, what we have to do is we have to draw a common tangent, and this we have done. So this is the envelope. So to make a gist, AJKP is the incident wavefront and the reflected wavefront is DGFE. Now this diagram looks a bit complicated because we have drawn or tried to draw all the secondary spheres and we have taken so many points. Let us draw it in a more simpler manner. So let us focus attention to the simplified diagram, which is essentially the previous one, and here IA is the ray advancing forward and AP is the incident wavefront. Now P goes to D in time V3 delta t, and in the same time A will send out waves over a sphere having radius of this amount, which is also V3 delta t. And the next procedure is Huygens construction to develop the envelope, and the envelope is DE as before. So this is the incident wavefront and this is the reflected wavefront. Also AN1 is the normal to this reflector with which the ray makes an angle I, and this is the incident wavefront which makes angle I with the reflector. It's the same thing, and also if we look at the angles we find that this is 90 degrees, this is also 90 degrees, and therefore this angle and that angle are same, which is the angle of incidence. In a similar way, if we focus attention to this point, we find that this is the normal to the reflector, this is the reflected ray, and this is the reflected wavefront as specified. The reflected wavefront makes angle R with reflector, the same angle which this ray makes with the normal. And also if we study the angles we find that these two angles are same. Now it is our task to prove that this and that angle are same. Now this is an easy task if we focus attention to these two triangles. What we have stated in this diagram is written in a nutshell here. Here we have made a gist of things. Now let us focus attention to the triangle ABD, and we will calculate sin I from here. So sin of I is the perpendicular by the hypotenuse, so it is PD by AD, and PD is V3 delta T. And again from the triangle AED, this is 90 degrees because this is the tangent and this is the radius, so it is 90 degrees. Now sin of R is perpendicular AE divided by the hypotenuse, that is AD, and AE is V3 delta T. Now it is time to take the ratio of sin I by sin R, and if we take the ratio of sin I by sin R, these sides being equal, we have sin I equal to sin R, from which we get simply I equal to R. Now further, so the first law is proved, law of reflection. Also, if we look at the rays IA, it is perpendicular to this incident wave front. This angle is 90, and similarly the reflected ray DR1 is perpendicular to DE, which is the reflected wave front, or rather ED, because this is 90 degrees. And also AN1 or DN2, they are perpendicular to the mirror reflector. Again, AP is perpendicular to the plane of the paper. ED is perpendicular to the plane of the paper, representing wavefront, reflected wavefront, and the mirror M1, M2, they are perpendicular to the plane of the paper. And this means this set IA, DR1 and AN1, or the normals, they lie in the plane of the paper or coplanar. So law of reflection has been proved. Let us consider the application of Huygens principle in the case of light passing through an aperture, and the aperture in our diagram will denote by AB. So let us concentrate on the first figure. Here the source is at infinite distance and therefore the rays are parallel. This is the direction of propagation, and the wavefronts are plane wavefronts. Now this is a representative wavefront, and from this wavefront we can build the future wavefront by Huygens principle. We can draw the half spheres, and then we can draw the common tangent or envelope to get another wavefront, which is also plane wavefront. Now this plane wavefront advances and it impinges on this arrangement, which has an opening which is defined as aperture, and this portion is blocked. This portion is also opaque. Obviously these opaque portions will not allow the wavefront to proceed any further, but this being a opening or an aperture, this will allow light to enter into the right side of it. Now what is the mechanism of entry of light through this aperture? This can be obtained by Huygens principle. The plane wavefront that sits here or that arrives here has innumerable points between A and B, and each point is a source of secondary wavelets, and we have drawn these secondary wavelets in this following manner. So this is a half sphere, this is another half sphere which is emitted by a point sitting here, and this point which is at the end point, this also emits another half sphere secondary wavelet. Now this is the common tangent and the envelope, and therefore if we draw the full envelope we get this one. So this is the resulting surface. Now this resulting surface has two portions. One is the plane portion and the other is the curved portion. If we go over to the next figure, similar analysis also shows that we end up with a plane portion and the end portions are curved, in contrast to the incident plane wavefront, which is infinitely extended on the upward region as well as on the bottom side. If we go over to the next figure, we find that we have a larger aperture and a larger amount of plane portion, but still we have a curved portion. Let us briefly recall what the situation would be if we use the ray diagram to explain the same thing. So in this case, this is the arrangement and this is the aperture. These are opaque spaces. Light enters from left to right. It just moves on in a straight line, and in that situation we'll have a shadow here, geometrical shadow, here also a geometrical shadow, and this would be the illuminated region. But what is observed in an experiment is that light enters into this shadow. Now, the mechanism of which we are not able to explain with the help of this ray picture. Light enters into shadow, there is blurring, and therefore we are trying to explain such blurring effect or such intrusion of light into the shadow region with the help of Huygens principle. So this is what we have. The source is at the left and the plane waves are advancing. It encounters an aperture. The picture shows how we get the successive wavefronts through Huygens construction. These are the secondary waves in the form of spheres, and these are the common tangent. This is the resultant curve or surface, and this is how the wave propagates. Now the important fact is that there is bending here. There is a curved portion here. Here on the left side, in the case of incident plane waves, we have straight lines which represent plane wavefronts. Here too we have straight lines, but in the end we have curved regions. So in a nutshell, we find that the resultant wave pattern which we get after plane wave moves through the aperture is that it has two portions. One is the plane wave part and the other is the spherical wave part. Now this is the, as shown in the previous diagram, this should have been the illuminated region and this should have been the geometrical shadow region. But as light bends, as evident from this diagram, this portion will be illuminated. So actually light goes into the geometrical shadow, and the mechanism is very clear if we apply Huygens principle to it. If the aperture is large, we have a plane wave part and a curved part. But if the aperture is very small, then what happens is, even if the incident wavefronts are plane waves, after it goes through the aperture, on this side we have spherical waves. So transmitted spherical wavefronts are obtained, and such bending of light is known as diffraction, and this has been done using Huygens principle. So we have been able to describe how light moves into the geometrical shadow region using Huygens principle. Let us consider light passing through two apertures, and we'll analyze such passage of light through two apertures by the application of Huygens principle. At the very outset, let us mention that a transverse wave propagates as a series of crests and troughs. Crests are the locus of maximum positive displacements, while troughs represent the locus of maximum negative displacements. Now let us concentrate on this diagram where we have shown two apertures and they are named S1 and S2. Source is far off on the left side and parallel rays are emerging from the source and they impinge on these two apertures, and it comes from a long distance, which means we have plane wavefronts. So these are plane wavefronts, and we have a series of troughs and crests. Now after impinging to this arrangement which has two apertures, what we have from each of the two apertures is shown in this diagram, which we discussed a few while back. So each source will set out a set of spherical waves. So this set of spherical waves correspond to this aperture called S1, while this set of spherical waves correspond to this aperture which is named S2. Now let us study this diagram minutely. If we proceed along this line, we find that at this point there is superposition of this trough of S1 with the trough of S2. Here we have superposition of crest of S1 with crest of S2, while at this point again troughs of both meet, and at this point crests of both sources meet. So this line corresponds to maximum points. On the other hand, this adjacent line, if studied minutely, we find that trough of S1 meets a crest of S2. At this point, crest of S1 meets a trough of S2, while here a trough of S1 meets crest of S2, and so on. So these are points of minima, while here too we find that the trough of S2 meets crest of S1. Here trough of S1 meets crest of S2, and so on. So these are points of minima. Again, if we look at the adjacent line here, we find crests of S1, S2 are meeting here, while troughs of S1, S2 meeting here. So this again correspond to points of maxima. Here also the same thing occurs because crests of both meet while troughs of both meet here. The adjacent line again here corresponds to crest of one meeting with trough of the other, and here too the same thing. So this is one minima, this is a maxima, this is again a minimum and again a maximum, and here again a minimum, then maximum, then minimum, and so on and so forth. So if we place a screen here, we can suppose that we might have an intensity variation because we expect maxima to give rise to brightness and minima would give rise to low intensity or darkness. The description that we presented is written over here. Now let us revert back to this figure. Three things are to be stated. The first one is a remarkable feature that even if the incident wave is plane, on entering into this aperture we have spherical waves. So plane waves give rise to spherical waves after they pass through a hole. Secondly, in both the diagrams, bending of light is very evident, and this phenomena is called diffraction. And thirdly, if we look at this figure, we find that there are two sets of waves, one emerging from S1, the other one emerging from S2. And from this description, it follows that they superpose, and superposition might give an intensity variation. Now this was actually studied in 1801 by Thomas Young, and we'll describe that experiment in a future lecture, lecture 3A. So to end up, let's go to a quote of Aristotle, the famous philosopher. Patience is bitter, but its fruit is sweet. Only people who are patient, who are devoted, who are sincere can flourish in our subject, which is called physics. Thank you.